We are looking at a section on exponential functions. We have previously worked with exponential expressions where the exponent was a rational number. And so in this section, we will deal more with solving equations and also looking at some word problems, application problems. The expression b to the power x can actually be defined for all real numbers x, including irrational numbers. An exponential function is of the form f of x equals b to the power x. There are some restrictions of what b and x can be. B has to be greater than 0, and it cannot be 1, because if b is 1, we would have a constant function instead of an exponential function. And x can be a real number. And these are just some examples of what exponential functions look like 3 to the power x. Notice 3 is the b value, and it is not 0, and it's greater than, it's not 1, it's greater than 0, and it can be a fraction, 1/2. It still is within the restricted parameter. Once you graph exponential functions, these are true here. These are the properties of exponential functions. First, it is a one-to-one function, so therefore it has an inverse. And the y-intercept is 0, 1. And there's no x-intercept. And the domain, which means all the x values, is negative to positive infinity. And the range is from 0 to infinity. Here's an example of a graph of an exponential function where the base, which is the b value, is greater than 1. So you see that there's exponential growth, right? So as you move from left to right, it is going up. And when the b value is between 0 to 1, meaning it's a fraction smaller than 1, then we have this case where you're moving from left to right, it's going down. So we have what we would describe in general as exponential decay. The uniqueness property of b to the x, which will help us solve equations, and that's what we're going to be looking at now. This property just says if b is greater than 0 and b is not 1, then b to the x equals b to the y is equivalent to saying x is equal to y. This is just saying that if the bases are the same, then the exponents have to be the same. For example, if we wanted to solve 6 to the x power equals 36, notice on the left-hand side, the base is 6, so I would want to make the right having the base 6 as well. So you would write 36 as 6 squared. So notice that the bases both on the left and right are the same. Therefore, the exponents have to be the same. So we've solved it. X equals 2. Here's another example. 1 over 27, and then on the right-hand side, it says equal to 3 to the 2x. So you see the base being 3, so can you think of how to write 1 over 27 having the base of 3? Okay, good. It's 3 to the negative 3. Notice the bases are the same, being 3, so therefore the exponents have to be the same. And we're solving for x, so divide both sides by 2, and there you go. The solution is negative 3/2. Okay, so let's look at another, one more example. It's 4 to the 3x minus 6 equals 32 to the power 2x. So the key to this problem is to rewrite both the left and the right-hand side so the bases are the same. Since 4 is 2 squared, we'd write 2 to the power 2 times 3x minus 6, and then do the same trick on the right-hand side. We multiply it out. Notice the 2 in the exponent gets distributed to the 3x minus 6 to get 6x minus 12. And then on the right-hand side, it's 2 to the 5th power to the power 2x, so multiply the 5 and the 2 to give us the 10x in the exponent. Notice again that pattern, the bases are the same, the base being 2, so we can set the exponents to equal to each other. And then we solve for x. And we get the solution -3. We'll look at some application problems. Many real-life application problems use exponential functions, and there are plenty of examples here. We'll look at one particular type dealing with compound interest and also exponential growth and decay. So if you don't have your calculator with you, pause the video, go grab your cool piece of technology so we can do this part. So here's the problem. Find the total amount invested in a savings account if $5,000 was invested and earned 6% compounded monthly for 18 years. Underline the words compounded monthly. That's a clue, and that tells us which formula we need to use. In this case, we need to use the compound interest formula. And then we're going to round our answer to 2 decimal places. So this is the formula we need. And of course, just like any formula, we need to recognize what the variables stand for. So pay attention that P is the initial principal invested, R is the interest rate. In this case, we want to make sure that we put it in a decimal form when we do our calculation. And then N is the number of times interest is compounded each year, and T is the time of the investment, and A is the final amount of the money that's in your account. So looking at that formula and then looking at the problem, can you go ahead and figure out what values are given? For example, what is P? What is R? What is N? And what is T? So P is 5,000. The rate 6% put in a decimal form will give us 0.06. And then N has to do with the number of compoundings and is compounded monthly. And since we're talking about the interest per year, compounded monthly, so that's 12 months a year. So the N value is 12, and the time of the investment in years, in this case, is 18. Okay, so we're going to plug those values into our formula. So you would want to jot those values down and plug these guys in the formula, and it looks like that. So now you're going to get your calculator out, and you're going to punch in 5,000 parentheses, and then this whole part raised to the power 12 times 18. The other way that you can do it is break the problem down a little bit before you put in the calculator. For example, in this case, we can take 0.06 divided by 12 to get 0.005, and then you can add the parentheses, add inside the parentheses 1 plus 0.005. And then in this case, you can take from this to the last step, you can take 1.005 raised to the power, remember that raised to the power 2 key, 216, take that result times 5,000. Hey, not bad. So if you're parking your money $5,000 at 6% for 18 years, you come out with a balance of close to $15,000. That's a pretty good gain for doing nothing with your money, just parking it there in a savings account. Okay, so here's another problem that you can try, and this one has to do with continuous growth. And this is the formula for it. I will leave this for you to try. Enter that in the calculator, and it was asking for radioactive decay after so many years. What is the balance? And the answer is 22.54 grams. You will need a calculator. Okay, so make sure you have a calculator with you. Either a scientific calculator or a graphing calculator will work for this problem. And that's it for now. I hope you enjoyed working with exponential functions. Hopefully it's all thumbs up from here and you have lots of fun with lots of homework problems. Next time we will be exploring logarithmic functions. That's a lot of fun. All right, see ya.